Welcome learners. Today we are going to discuss about Sturm-Liouville's boundary value problem. Basically we are going to learn about what is the Sturm-Liouville's boundary value problem and how we can identify this type of problems by observing the form of the equations, how we can solve these equations, and what are the properties of the solutions this equation produce, and what are the characteristics functions, and what are the characteristics parameters. And we can see that how we can define these parameters and these functions while we are trying to solve the Sturm-Liouville's boundary value problems. We will also see how we can develop Fourier series and a technique to expand a function in terms of these characteristics functions which are produced by this solution of this Sturm-Liouville's boundary value problem. Okay, with this brief introduction, let's start. So, you see, this is the Sturm-Liouville's problem. So, basically, this is a self-adjoint equation where we can see this px has a continuous derivative, since we need to differentiate it so that it should satisfy this equation. So this equation should be well defined. For that, this px should be differentiable and continuous. Similarly, qx and rx should be continuous, and lambda is the parameter. Okay, so the lambda is a constant, but we can choose value, and these parameters will get different equations depending on these different values of parameters. So when we are going to solve this equation, we'll see these parameters actually play a major role while we are going to solve this equation. And why it is called boundary value problem? Because with this equation we have this boundary condition. We can see this is a mixed boundary condition where the initial point of the interval. So this equation is defined in the interval a less than equal to t less than equal to b. So in this interval, this problem is well defined. Now, so when we are trying to define this boundary value, so you can see both the points has been used, a and b. So that's why we call this mixed boundary value problem. So that's why that this problem, that means this equation with these boundary conditions, is called Sturm-Liouville's boundary value problem. Let's see some examples. So see, this is the first example where our px is 1 and qx is 1 and qx is 0 and rx is 1, and here is the lambda. So and this is the boundary condition. So this equation is defined for the closed interval 0, pi, and this is another equation where this is the mixed boundary condition, and this is the equation where we can see, so this is your px, this is your qx, and this x square is your rx. Okay, so now we are going to try to solve this boundary value problem, which is basically, you can also observe, so all these equations are basically self-adjoint equations, which you can find under Sturm theory. So let's move on. Here we are trying to solve the first example. So let's see how we can solve this. Now if our lambda, this lambda is 0, if lambda is 0, so then obviously y equal to c1 plus c2x. And now if you use these boundary conditions, you will get y equal to 0. So these are trivial solutions. Since we know all homogeneous differential equations satisfied by the trivial solutions, so our main motive to solve a differential equation is to find non-trivial solutions. So now, so we are not interested to find this trivial solution. We want to find some non-trivial solutions. So let's move on to the second case where we have taken lambda negative. So if lambda equal to negative, so if you solve this equation, you will get this solution. So this is easily solvable. These are all linear differential equation. So obviously this one is linear differential equation with constant coefficients. We can easily solve, and we know from our graduation knowledge how we can solve it. So we are not going in details of the solution procedure. So but we are interested in the theory, that what are the properties these solutions have. So for that we are just concentrating on the solution. So this is your solution for lambda less than 0. So when lambda less than 0, you will get this y equal to C1 plus e to the power minus root over minus lambda x plus C2 e to the power minus root over minus lambda x. So this is your solution. Now if you use the boundary condition, you will get this C1 plus C2 equal to 0. You will also get this. Okay. Now if C1 is, now we are trying to find out the values of C1 and C2. Now how we can find out? So if the C1 C2 have to non-zero, then obviously this they have to be independent. So if they are independent, then both the solutions, they are only unique solutions, and that is 0. So we know now, that's why we have determined this determinant. Now we see this determinant is non-zero. Since this is non-zero, for lambda not equal to 0, obviously this is the case while lambda not equal to 0. Therefore, only option we have, that is C1 and C2, both are 0. Okay. So therefore, here also we are getting y equal to 0, a trivial solutions. So then again we are trying to find out non-trivial solutions. So let's move to the another case. So we can see lambda can possible have 3 possible values. Either it is 0, it is negative, or it should be positive. So if lambda is positive, what we have? We have these solutions. Now again use the boundary condition. When we will use this boundary condition, at y at 0 equal to 0, you will get C2 equal to 0. Now again use another boundary condition, that y at pi equal to 0. So from there you get C1 into this thing equal to 0. Again, if we have already gotten that C2 is 0. Again, if C1 is also 0, this will lead to non-trivial, a trivial solution, that is y equal to 0. We are not interested in that. So since we are trying to find a non-trivial solution, we are assuming C1 is non-zero. So C1 is non-zero for non-trivial solution. If C1 is non-zero, then this should be 0. So that's why sine of root over lambda into pi, this should be 0. And we know the sine of x should be 0 if x is equal to n pi. So from there we have root over lambda equal to n, where n is any integers. Okay. So from there we have lambda equal to n square. So root over lambda is n, so lambda equal to n square. Now this is your lambda. So for each lambda equal to n square, you will get a solution. This, where these cn's are non-zero. So this is your final solution, y equal to cn sine nx. So each of them is a solution. For each n, for each lambda, you will get a solution cn. So what is the ultimate solution? The final solution will be summation of them. Okay. So this is a example where we have solved a Sturm-Liouville's boundary value problem. We'll use this solution in the next theory and see how this solution can provide us various interesting results. Okay. So what is characteristics values and characteristics function? We have already seen the examples. The values of the parameter lambda, for which there is non-trivial solutions of the Sturm-Liouville's problem. So we have already seen that lambda, if you take any value of lambda, it will always not lead to non-trivial solution. In the last case we have seen, the last example we have seen that for lambda greater than 0, we have only find out non-trivial solutions. So for the values of lambda for which we have non-trivial solutions, those values of lambda are called characteristics values, and the corresponding solutions are characteristics functions. Okay. So if you want to see the example, just see the previous example. So here for this example, this lambda matlab n square, this n squares are your characteristics values, and this cn sine nx, for each n you have this function. So this is your characteristics functions. Okay. So next let's see an interesting theorem. What is this theorem? This theorem has basically 3 interesting results. So if there exists, so what is this theorem states? This theorem states, if you have an Sturm-Liouville's boundary value problem, then there will be always infinite number of characteristics values. Okay, one thing. And another is, this infinite number of characteristics values can be arranged in a way so that they can be written in monotonic increasing sequence. So see, we have written. So you can arrange this lambda such a way that you will able to write them in this manner, and this lambda n tends to infinity as n tends to infinity. This is the first result. Again, if you want to tally it with our examples, you can see here your lambda is n square. Okay, so as n tends to infinity, this goes to infinity, and for n equal to 1, 2, 3, these are all monotonically increasing. Okay, now let's see the second result. Corresponding to each characteristics value lambda n, there exists a non-parameter family of characteristics function. That also we have seen in the last example also, that there was our phi n was Cn sin nx. Each of these characteristics function is defined on this interval, and any two characteristics function corresponding to the same characteristics values are non-zero constant multiple of each other. Obviously, for a particular lambda, if you can get two different solutions, but they will be always multiple of each other. Since we have seen there is always a constant multiplication, so constant multiplication, like we have phi n equal to Cn sin nx. So this Cn is constant, so it can be any constant. So obviously one can take 1 in place of Cn, anyone can take 2. So it is a fixed constant. Okay, but this constant may vary depending on the situation or your boundary conditions. So if you each of these characteristics functions, so when you have a characteristics function and if you take any constant multiple of the characteristics function, that will be also be a characteristics function. So for each characteristics function defined on this, any two characteristics function corresponding to the same characteristics values are actually multiple of each other. So for a particular characteristics value, you will always have a characteristics function, and if you take any constant multiple of this characteristics function, that will also be a characteristics function for this characteristics value. And this third result is, for each characteristics function phi n corresponding to the characteristics value lambda n has exactly n minus 1 zeros in the open interval. So in the last example we have seen, let's see what we have, how we can tally this theorem with our last example. So this is what we have solved till now in the last example, and this is your characteristics values, and this is your characteristics functions. Okay, now this is your final solutions. Okay, now the last theorem, the third part of the theorem says that this phi n, if we equate it 0, it has n minus 1 number of 0. If you take phi 2, you will get 1 0. If you take phi 3, you will get 2 zeros. So phi n has n minus 1 number of zeros. We have to prove that. Okay, so this is our phi n from this. For this example, we are just varying these theorems for a particular example. We are not going in details proof of these theorems. It is very complicated and out of scope for this literature, but we are only interested to know about this theorem and understand them, so then we can apply it further. Okay, so this is your phi n. If you equate to 0, you will get Cn sin nx equal to 0, and this implies nx equal to k pi, where k is a constant, any integers. So these are in 0, plus, minus 1, you can take any values. You will always get a solution. For each x, you will get a solution. So what is we have? We have x equal to k pi by n. Now we will know that whatever value you take is a multiple of pi. K is a multiple of pi. Okay, so when n crosses, so if you put just value of n plus 1 here, it will obviously lead to pi plus pi plus pi by n. Okay, so it will repeat its value. It is a cycle. So this is in 12 standard. When we solve this trigonometric functions, we know that it's just repeat its values. Okay, so after this cycle, so how many independent solution you will get? You will get how many different solution, actually not independent, how many different solution you will get? You will get for x equal to this for 1, 2, 3, n minus 1. When you will put n, you will get the same value of x when you will put n in place of k. So basically k equal to 1, putting the value of k equal to 1 and putting the value of k equal to n are same for this trigonometric. They are different as a x, they are different, but you will put when they will produce the same things. Okay, so basically there are this many roots. Okay, so that's why, so this function has actually n minus 1 number of zeros. So this is, we can verify from this example. Okay, so let's understand what is normalized function. So we are just trying to read or trying to recall some of our knowledge so that we can use it. So normalized function is the definition we are just recalling here. What is the normalized function? If you integrate, so this is the domain of definition of the function. Now if you integrate with respect to the domain of definition with respect to n multiplied by some weight, this Rx is a known function weight. Okay, so a function f is called normalized with respect to the weight function r on this domain of definition if and only if this equal to 1. Okay, so in general, maybe most of us have seen that Rs, generally we take Rs equal to 1, but it may be more than any function of x rather than a constant 1. So this is the general definition of normalized function. Next, what is orthogonal systems? So suppose you have this sequence of infinite, this set of infinite functions, and this they will be set orthogonal if you again calculate this integration, and for m and n, m not equal to m, if it leads to 0, and for m equal to n, then it leads to 1. So we will say it's an orthonormal. So if it only the first property for different phi, if you get 0, then we'll say orthogonal system. And again, it will combine it with our with our normal function, definition of normal function, where if we take m equal to n and it leads to 1, then we'll say if you combine these two properties, then we'll say this is orthonormal function. So there is two property. One is this is orthogonal system, and another is it is a normalized function. Okay, so this is function is normalized and the system is orthogonal. That means if you take any two different function and integrate with respect to this weight, it will lead to 0. So if you combine these two definition, you will get this definition under this integration for this different result. When m not equal to n, it will lead to 0. When m equal to n, it will lead to 1. And then we'll say this set of function is a orthonormal set of functions. Now let's see how we can build orthogonal and then orthonormal characteristics function. So first we are trying to create a orthonormal set of characteristics function. We have already seen in the previous example that what are phi n's for particular example. So phi n is the characteristics function. That means these are the solution of the Sturm-Liouville's boundary problem for each characteristics value lambda n. So for each lambda n you have a phi n. Now if we multiply this phi n with a constant, it will again be a characteristics function for this phi n. Okay, so that we have seen in the result 2 of our first theorem. So this now we are just multiplying this kn for each phi n. We are multiplying with a constant so that this phi n becomes orthonormal. So these were our characteristics function, and after a slight modification, this is our new characteristics function where we have multiplied each function with a constant k1, k2, k3, etc. And this k, we have to find the values of k1, k2 and k3 in such a way that they become orthogonal. Okay, so how we can find it? Okay, so we want to make them orthogonal, so that's why we will use this definition. So first we are trying to make them normal. Okay, first we are trying to make them normal. So you are just taking two repeating same functions and with respect to, so as per the definition of normal function, this should become 1. Okay, so when this integration will become 1, so suppose this integration is greater than 0 but it is not equal to 1. Okay, so this it will give you some real value, it will lead you some value, and suppose this value is kn. Okay, now if we just divide by this, since this is a non-zero, we can divide it. So if you divide by this, the right side will become 1, and this is our new functions. Okay, so this is actually our constant. Now if you take this as a constant, so what is kn? Kn is basically this integration. Okay, so this is the modification. So if we modify this, the whole system of characteristics functions will become orthonormal set with respect to r. Okay. Okay. So now, as we have learned about normal functions, then orthonormal functions, and then we have learned how we can make our characteristics function orthonormal by slightly modifying them. Now we are going to use all this knowledge in this form of a theorem. So suppose this lambda n's be infinite set of characteristics values, and you have and we can write them in monotonically increasing sequence as we have seen in the first theorem, and this is your phi n is the corresponding orthonormal characteristics function. We are assuming these are orthonormal. So if you don't have orthonormal, you can always make them orthonormal by multiplying some constant that we have seen. So after multiplying, we assume this is a final orthonormal set of characteristics functions. Okay, and this point 2, let f be a function with continuous interval. So this f has some properties. We'll see why these properties are required. Okay, then we are saying f can be written in this form of this series, where this Cn is given by these functions. Okay, so obviously if you try to calculate this Cn, since they are orthonormal, so they are orthogonal also. So since they are orthogonal, so we can use the property of orthogonal. So from there you will get this. Okay, so except if you multiply by phi n, except this Cn, all the other coefficient will vanish as they are orthogonal. So you'll left with this. This is very easy. Now why we need these properties of this function? So that this integral becomes well defined. So the function f, which is continuous on the interval, it should be continuous and has a piecewise continuous derivative f dash on this b, and such that f of a equal to 0 if phi on a equal to 0 and f of b equal to 0 if this. So if this is 0, then we record this condition. If this is 0, then we record this condition. If f is non-zero at a and non-zero at b, then we don't need to worry about these conditions. When we'll prove this, if we try to prove this, we'll see this will help you to prove. And first it have to be continuous, because this have to be well defined. So whenever you see, so we are putting some restriction for some particular function, we will always try to find out why, because we need this property so that we can prove the result, or we are going to use it. Okay, so this is an important theorem which leads to one important application, that any continuous function with these properties can be expanded in this form of a series. Okay, so this looks like similar to our Fourier series knowledge. So from here we get the idea of Fourier series actually. So next we see this is a definition of Fourier series. Whatever we have seen in the last theorem, so let this is be say orthonormal system with respect to a weight function r in this interval, and if a function f be a function such that with product this is integrable. So see, this is integrable, this should be integrable. So that's why we need all those good properties of the function. Here they didn't write all these good property of function, they have directly written this is integrable, that's enough. Okay, so that this product, so the function f be such way that this should be integrable. So it helps us out so that we don't mention all these properties which are lengthy or difficult to understand, initially difficult to understand. Okay, so this series, so f can be written in this form of series, the coefficients are given in this form, and this series is called actually Fourier series, and these coefficients are called Fourier constants. If you write, if you take this phi n in the form of your known Fourier constants, Fourier functions, that is cos and sine, then it will become our known trigonometric Fourier series. Okay, so this is what we have seen right now. So thank you. So what we have seen today, we have seen what is Sturm-Liouville's boundary value problem, how we can solve it, and how we can define characteristics function and characteristics values from the solution of Sturm-Liouville's boundary problem, and how it help us to create a set of orthogonal functions, infinite a set of infinite orthogonal functions, and which leads to create Fourier series expansion of a known function. So with this summary, we again thank you all for giving your precious time. Namaskar.